Hello everyone. Today I'm going to be covering problem 25.31 on mastering physics. We're given this figure here and asks, what is the electric potential at the point indicated with a dot in the figure? So what we're given is a triangle of charges here. This dot in the center is where we're trying to find the electric potential at. So our knowns from this are Q1, label this bottom left hand charge, as negative 2.0 nanocoulombs. Q2 is negative 2.0 nanocoulombs, and Q3 at the top is 1.0 nanocoulombs. We can go ahead and convert those immediately into coulombs, and that would be negative 2.0 times 10 to the negative 9 coulombs, and 1.0 times 10 to the negative 9 coulombs. We're also given the distance between each charge at 3.0 centimeters, which of course is 0.03 meters. The important equations that we're going to be using in this is the electric potential equals the sum of KQI over RI. Now we can't use the 3.0 centimeters as our radius because we're not trying to find the electric potential at any of these corners of the triangle. So what we have to do is go back to trigonometry and think about equilateral triangles. So if you take from the vertice and draw a line to the center of each leg of the triangle, you will intersect here at the center. That creates a series of right triangles. And we can translate this smaller triangle here down to this bottom part. You'll notice that these H1, H2, and H3 are all going to be equivalent since the triangles are all equivalent. So what we can do to find the value of this H1 is to use cosine. And remember that cosine is equal to adjacent over hypotenuse. So let's say cosine of theta equals adjacent over hypotenuse. Now we can do a little bit of algebra, move the h over, so we have h cosine theta equals adjacent. Then divide cosine theta over, h equals a over cosine theta. Then plugging in our giving numbers, we're going to have h equals 1.5 centimeters. Since we cut this bottom length in half, we're going to have 1.5 centimeters over the cosine of 30 degrees. The reason for 30 degrees is when you have an equilateral triangle, you have 60 degrees in each vertice. So dividing that vertice by 2, you're going to get 30 degrees. If you plug this into your calculator, you're going to get about 1.732, or you can just keep it as the square root of 3 if you want to be exact. Square root of 3 centimeters. Now, of course, in our equations, we're going to be needing to use meters. So if you divide this by 100, you're going to go back to meters. So we have root 3 over 100 meters. That is going to be our radius from the center point to each of the 3 charges. Now what we can do is go back and use our equation that we talked about in the beginning. So once again, the equation is the electric potential equals the sum of KQI over RI. Since we already said that the legs of each of those right triangles are equivalent, we can just go ahead and call them R to satisfy the equation. That'll simplify our work a little bit. So let's rewrite this equation to a more simpler form. So we have V equals K. We're going to pull this out because it's going to be multiplied throughout each term, so we'll factor it out. Then we're going to have Q1 plus Q2 plus Q3. And again, we can place these all over R since the H's are equivalent in our diagram. Alright, so now what we need to do is just basically plug in our numbers at this point. So V equals the Coulomb's law constant, which is 9.0 times 10 to the 9 times our charges. Q1 was negative 2.0 times 10 to the negative 9 coulombs plus negative 2.0 times 10 to the negative 9 coulombs for Q2. And then Q3 was 1.0 times 10 to the negative 9 coulombs. And we're dividing this whole thing by the square root of 3 over 100. Plugging that into your calculator, you're going to get the electric potential equals negative 1558.84527. Sorry, 5727. But since we're only given two significant figures in the original part of the problem, we're going to go ahead and round that up to V equals negative 1600. Okay, now we have a final answer of negative 1600 volts. So what we're going to do now is take a look at the contour map to see if this makes sense. So down here at the bottom of the triangle, we have two charges of negative 2 nanocoulombs apiece. So that means that they're going to be taking up a lot of the electric potential in this area, while we have the positive 1 nanocoulomb charge at the top. Now the difference here is 3 nanocoulombs between the two, so these are going to have a lot more electric potential around them than this one will. So this point here is pretty obvious that it's going to be negative, because if we look from here where the electric potential is very negative and move towards the positive charge, we're going to reach 0 electric potential right about here, 0 volts. So this portion is still very much in the negative side. So a final answer of negative 1600 volts is pretty reasonable for this situation. Well, I hope you guys have a nice night. Thank you for watching.